relativistic quantum field theory in the very simple example of the scalar free field that you have been quantizing using the canonical formalism in the QFT1 lecture. Okay, but let's first discuss a few other points that will be important in the rest of the lecture about the path integral formalism. And in fact, we realized with Dan that if I had explained the first point at the end of my last lecture as this was scheduled, you would have found the tutorial less difficult. So I apologize, but I think now you will understand, if you had not grasped all the aspects, what was going on, and you will see that, in fact, once you have understood the idea, the calculations are very simple. Okay, so the first, so the first point that I want to discuss is how to introduce operators, how to describe operators, and namely observable, and not only the evolution operator, in the path integral formalism. And for that, and the second point will be the discussion about the vacuum state, how you construct the vacuum state, the ground state of a system using the path integral formalism. So first, operators. For that, I need to recall you something that I am sure you know, which is a bit subtle point, which is the two possible descriptions of quantum states and quantum operator that are called the Schrödinger picture and the Heisenberg picture, which are just basically two equivalent ways to describe quantum states and quantum observables simply by a change of basis of the Hilbert space. So remember, let's start from our good old system. We have a particle on a one-dimensional line described by this Hamiltonian. And the evolution operator, u of t, is simply exponential of t over I h bar times the Hamiltonian. Okay? So in the Schrödinger picture, it is a picture that you use everywhere in non-relativistic quantum mechanics, in quantum information. You consider that quantum states are described by vectors in an Hilbert space, so vector space, psi, that are independent of time. So a quantum state is described by a vector, a ket, in the Hilbert space, or your theory. A quantum observable is described by some operator. So this is a state, a vector, and this is an operator in the space, an operator acting on the Hilbert space. So it's an element of an algebra of operator defined on the Hilbert space. So let's call it, for instance, the algebra of operator, bounded operator of the Hilbert space. Okay, and of course, the evolution, the dynamics is described by the fact that states evolve with time, so that psi of t, if we start at time 0 by a quantum state psi, the state of the system at time t is described by another wave vector, psi of t, which is simply u of t psi. Okay? And in particular, taking the derivative of this with respect to t with the form of the evolution is equivalent to obtain the Schrödinger equation psi of t equal h times psi of t. This is the Schrödinger equation. Okay. In the Heisenberg picture, you change your point of view because simply you follow the states, all the states, as they evolve with time. So basically, you define a state psi at time t. You define it as simply u of minus t times the state psi. So this notation means simply that psi of t is a quantum state different from psi. It's a quantum state such that if you go backward in time evolution, at time 0, it's the state psi. Okay? And
can you explain that point again?
Pardon?
What did you say? I think, can you repeat that point, please? The point you just made.
This point is simply that, okay, apply, rather take this as a mathematical definition of this object. And you will see immediately what I meant when I will explain how the dynamics is described in this system. Okay. So you see, I make a change of variables, a change of basis on the Hilbert state by stating that at time t, I rotate all my state vectors by u minus t, namely by the, of course, u of minus t is just the adjoint of t, because u is a unitary operator. Okay. And you will see what I meant. Okay. So in this description, of course, I made just a change of basis on the quantum state. So I need to make the similar change of basis on the operator in order not to change the physics. You know, the physics in a quantum system is described by the fact by probability amplitudes, psi prime psi. Okay, and by, in particular, by matrix element of operators. And those are the numbers, the quantities that measure the physics, that give you the physics, that give you the probability transition. Okay? So if you apply this change of variables on the state vectors that describe the quantum state, you must do a similar transformation by stating that a given quantum observable is described by different operators when you consider a measurement of this observable at different times. Okay? And the relation is simply u of minus t a u of t. Okay? So here, in the Schrödinger picture, making a measurement on a quantum state at any time, possible time, is described by the same operator. In the Heisenberg picture, this is described by different operators. But those operators act on different wave vectors, because we made the rotation in wave vectors and the opposite rotation on the operator. So that, in fact, these scalar products and these matrix elements are unchanged in the Schrödinger and the Heisenberg picture. So the physics doesn't change. Okay. So now, with those two definitions, of course, you can check that, of course, u, the unitary operator, doesn't change because u commute with u. But in addition, consider now in the Heisenberg picture what is the state psi of t given by the evolution given by the Schrödinger equation in the Heisenberg picture. What is the wave vector that describes the state psi of t at time t? Okay, this is simply u of t of u of minus t of psi. So this is psi. So you see that in this Heisenberg picture, in general, the quantum state is described by different vector states, different vectors at different time, but the particular set of vector states given by the dynamical evolution of the system are described always by the same vector. Okay. So in this description, wave vectors do not evolve. Quantum states evolves, but the mathematical object that is a vector in a Hilbert space doesn't move. Okay, but the physics change of the states, the physical property of the states change. So, of course, what changes are the operators, the observable. So now the the Schrödinger equation is replaced by a Schrödinger equation for operators. And what is it? Well, we have this equation. We know what the time derivative of u of t is, so it's very easy to see that the evolution operator for a given observable, if you start from an observable that is time independent, it is described by an operator that is time dependent, but the evolution of this operator is simply minus the commutator of the Hamiltonian with a of t. So instead of having a linear evolution equation involving an operator applied on the vector state, you have a similar evolution operator involving the commutator of the Hamiltonian with the operator. Okay. So this Heisenberg picture, in fact, is not very natural. Well, it's useful in non-relativistic quantum mechanics, but it's very useful in quantum field theory, as we shall see at the end of the lecture. Why is it useful? It is useful because, you see, times appear as a parameter in the observable. So making an observation is different at different time is described by a different operator. And in a quantum field theory, we want to describe a physical system in a relativistically invariant way. So applying a measurement at different points of space must be described by different operators. But we know in special relativity that space and time mix. If you make a Lorentz boost, time and space changes. So you must treat time and space on the similar footing. So it's natural, since operator must depend on the point of space in which you apply them on your quantum field, it's natural that applying this quantum field at different times must be described by different operator if you want a description that can be covariant in some way. Okay, so it's natural. If you want to make quantum mechanics compatible with special relativity. Okay. And finally, one last remark. The fact that you can describe the state of a quantum system either by an object that evolves with time or with an object that doesn't evolve with time is not at all a quantum fantasy. It already exists in classical mechanics. And for instance, in classical hydrodynamics, if you want to describe the movement of a fluid, a classical fluid like water, it's known that there are two possible descriptions. One is called the Eulerian description of a fluid, and the other one is called the Lagrangian description of a fluid. In the Eulerian description, it's just the description that if you have a fluid, you have a little point x, and you see what is the speed of the fluid as a function of time. So you have a river, and you sit on the river, and you see, here there's something is going on. Here there is it's flow faster, it's flow slower, there is a eddy going on, etc. Okay, so this is Euler. In Lagrange, you are on a boat. You are flowing with the river, and you look around and you see, I'm going fast because the trees are going fast, or here there is something going on, there is an eddy. So here you are on the boat, and you move with the river, and you see what's going on. Okay, and those are two very useful descriptions for fluid dynamics, and even to do numerical simulations. Some numerical codes use the Euler description, and some numerical codes use the Lagrangian description. So Schrödinger picture and Heisenberg picture, that's exactly the same thing for a quantum system. Nothing else. Yes?
How did we end up with the total derivative in the evolution for the Heisenberg picture as opposed to a partial?
How do I?
How did we end up with the ddt as opposed to partial t?
This? Oh, I am sorry. I'm sorry. That's always. I'm sorry. That's the same derivative. Sorry. Okay. We'll have to be a bit careful when the Hamiltonian depends on time. Then you have to take into account partial and total derivative. But here, h is time independent. So everything is okay. Okay. So once we have that, let us go back to our problem of describing the probability amplitude for our system. Okay. This propagator, this matrix element of the evolution operator, which describes the probability amplitude for a particle, which is at time t1 at a position q1. If it is conditioned to be at time t2 at position q2, what is the probability amplitude for a quantum evolution for going that from that? Okay. We know that it is given by a path integral over all the possible histories weighted by exponential of I L bar top n. So this is given by integral d of q exponential of I over h bar s of q, the classical action for each trajectory with those boundary conditions. Okay. So now, using this definition of the states in the Schrödinger picture and the Heisenberg picture, of course, this is the way we write this probability amplitude. This is the probability amplitudes. It's a complex number that describes the physics. This is in Schrödinger picture, S. Okay. What does it correspond to in the Heisenberg picture? Simply to the scalar product of two states. The states Q2 at time T2 and the states Q1 at time T1. Okay. Just write U of T2 minus T1 as u of t2 times u of minus t1. Okay, and realize that this is u dagger of minus t2 times u of minus t1. And you get this. Okay, so that's just the same object written in the Heisenberg picture. Okay, at the transition probability, the scalar product of these states, initial states, with these states, final states. Here, the evolution operator has been included in the states. Okay, just change of notation, change of basis, same physics, same physical amplitude. Okay, so now, well, this is a probability amplitude, but let us ask what is a different object, which is the same functional integral, integral over d of q, exponential of I over h bar s of q, with this initial and final boundary condition. But now I measure this integral with an additional term, which is just q at some time t3, let us say. Well, let me call this q initial, q final. This is q initial, q final. So let me call this q of t1 to distinguish. So this is t initial, t final, q initial, q final. Initial condition, final condition. Okay? So, what gives this calculation of this functional integral where you insert a q at some time t1? So you see at a time t1 here, I measure the position of the particle, the fictitious particle that evolves in the path integral. So as you see, this is a classical measurement. This is a classical real number. So this is not a quantum measurement at all. I'm not making a quantum measurement on the particle. I'm just computing a path integral. Okay? So not a quantum measurement. We are doing some math. We are doing a calculation. Okay. So in order to do what this gives, it's quite easy. We can write this as, decompose that into two functional integrals. We can write this by first integrating over this position of the particle at time q t1. Yeah. We say that q at time t1 is some q1. Okay. And I write this as an integral over dq1. So, and once I have fixed q1, I sum over all the paths which goes from q initial to q1. This is now q1. Times all the paths that goes from q1 to qf. So I rewrite this simply as then integral over all the q's such that q at time t initial is q initial and q at time t1 is called q1, exponential of I over h bar s of q. But s of q for this first part of a trajectory, and then I sum over the second part. So I write times integral over dq from q at time t1 equal q1 to q at time t2 and t final equal q final of a same phase factor. Okay, but this is the phase factor for the first part of the trajectory. And the second one is the phase factor, the action for the second trajectory. Okay. So, and of course, then I have Q of T1. Okay. But now, this is a path integral that gives something like that. This is another path integral that gives another probability amplitude. So what is this? This is integral over dq1. The probability amplitude to go from q, so let us write it in the opposite way. This is q final u of t2 of t final minus t1, q1. Q of T1 is equal to Q1, so I should have written this Q1. And this gives the probability amplitude Q1 U of T1 minus T initial Q initial. See? Very simple. But now, what is this object? This is nothing but the operator Q. Well, if I integrate, you see now you can integrate. Because you have the decomposition onto the position eigenstate of Q. This is just a diagonalization of the operator, the position operator. You see. So, this object here is nothing but QF U of TF minus T1, the operator Q times the evolution operator of T1 minus T initial times Q initial. Okay, so that's the way we wrote this matrix element of some operator in the Schrödinger picture. Schrödinger picture. But we use our definition of how to write things in the Heisenberg picture. This is nothing but the matrix element between the states Q initial at time initial and Q final at time final of the operator Q at time T1. Okay. So this path integral d of Q exponential I over h bar S of Q times Q at time T1 is just a way in path integral to represent the matrix element of this operator. So you see, you have it's a path integral version of the correspondence principle. Just correspondence principle in its path integral version, inserting classical inserting classical object position of the particle over which we sum its history in the path integral is equivalent to compute the matrix element of the quantum operator Q of T1. Quantum operator in Heisenberg picture. Okay? So you see, representing operator is quite simple, the path integral. But just to have to remember that when inserting operator, you represent operator in the Heisenberg picture. So that's one of the reasons why the Heisenberg picture is useful. It comes naturally in the path integral formulation. Okay? So I did that from, so Q in the path integral is in duality or represents the operator Q. Okay. Of course, you have other operator. So for instance, you have the operator P. So this is position. This is the impulsion. Well, it's slightly more complicated for the impulsion operator. But so I won't describe that at that stage. I will come back a little bit later. There are some subtleties. Not, yes?
Both the momentum and precision operators are unbounded operators, right?
Yes.
How does the path integral handle this?
It's just a mathematical subtlety because instead of considering Q, we could have considered a function f of Q bounded. It would have been exactly the same. And then we would be on safer ground. Okay? And well, the same for P once you know how to describe P. Okay? Yes?
So the function of an unbounded operator can be bounded itself?
Of course. Is a bounded function. Y versus Q. This is Q. It's an unbounded function. This is f of Q. It's a bounded function. It's vary between 0 and 1. In fact, there is a theorem which tells you that you can approximate in the sense of a well-defined topology on the space of function or on the space of operators. You can always approximate an bounded operator by a series of bounded operators. Okay? So it's an important mathematical point, but it's not at that stage of the discussion, it's not a physical problem. You have to be careful if you want to do proper mathematics. Okay? Good. So that's not completely the end of the story, because now you can do the same thing for two operators. Okay. So what happens now if I want to compute the path integral with the same boundary conditions, exponential of I over h bar s of q, then q at a time t1 and q at a time t2, with, of course, t1 and t2 in between t initial and t final. Okay? Well, you can play the same game simply because what you have to do now is to do a path integral from t initial to t final and measure the position at two t's. So this amounts to insert an operator q at each of the time. So it's very easy to see that this amounts to compute the matrix element of a more complicated operator, which is simply Q of T1 times Q of T2 in the Schrödinger picture. Okay. But you have to be a bit careful. You obtain this if first you compute the evolution from time T1 to time T2, then you obtain Q of T2. Then you compute the evolution between T2 and T1. Then you insert the operator Q at T1. Then you compute the evolution for T1 from Tf. So you obtain this operator with a proper boundary metric element if T1 is larger than T2. So we are in this solution. If T1 was smaller than T2, what we have been doing is that we would have computed first matrix element of Q of T1, then a matrix element of Q of T2. So we would have obtained Q of T2 times Q of T1. And those are different operators because in the Heisenberg picture, Q of T1 and Q of T2 do not commute because they are defined from the operator Q that commutes by applying the H. And this is a consequence of the fact that H and Q do not commute in the standard representation. H of Q is proportional to P, in fact. Okay, so this is different. And of course, they commute only when T1 equals T2, where you get the operator Q2, Q squared. Okay, so you see, the path integral, if you want, automatically order in time the operators. And this object, in fact, there is a mathematical definition of this object, which is just, by definition, let us call this the time-ordered product. Time-ordered product. T runs for time-ordered of the operator Q of T1 and Q of T2. So given two operators, whatever operator they are, in the Heisenberg picture, I define the time-ordered product of the operator at the larger time applied to the operator at the smallest time. So by definition, in fact, there is a general definition of the time order is the following. By definition, if you have any operator A of T1 and B of T2, they do not need to be necessarily the same. They do not need even to commute at equal time. The time-ordered product of A of T1 and B of T2 is by definition equal to A of T1 times B of T2, where this is a product in terms of operators. If T2 is less than T1, and this is B of T2, A of T1, if T1 is less than T2. Okay. You see, so that's the definition of a time-ordered product. And you see that for general operator, if A and B in the Schrödinger picture do not commute, this is not well defined at T1 equal T2. So there are subtleties. But this is well defined if T1 is different from T2. And that's all what we need. Okay. So it's easy to write a general correspondence principle which tells you how you construct the matrix element of some operator out of the functional integral. But when you apply products of operator at different time, then what you, well, products of Q at different time, what you obtain is an operator that is the time-ordered product of the two operators you have inserted. Okay, so that's something not very complicated, but you have to get used to it. Okay, and you will see later on that, in fact, there is a relation between time ordering. There is a relation with something that we call normal ordering of creation and annihilation operators that you have discussed in the QFT1 course. So, in fact, those concepts are not that unrelated, and I think you have already been introduced with time ordering. Okay, good. So that's 4.1a. I realize that I'm going a bit slow, but that's important to have understood that. Okay, so point 1b. Well, in high energy physics, in fact, one very important state is the vacuum state. Because in first approximation, we assume that the universe, if we don't do cosmology and consider the cosmological background, lives in its ground state, and there are some excitation. We are excitation of the ground state. But there is not matter everywhere. There is not an infinite density of energy in this room, which means that you have the first excited state of the field exists. We are those states. So it's quite important. Okay. So something important is the ground state. The ground state. And therefore, we are interested into what are the matrix elements of some operator A in the ground state. Okay. So how do you construct the ground state out of a functional integral? Well, to understand well what's going on, let us go back to Euclidean time. We'll just be doing some math at that stage. So let me do some math and okay. And let me compute. Remember that the evolution operator at some Euclidean time, tau, is just exponential of minus tau over h bar the Hamiltonian. So it's an operator. Assume that I am in the case of a particle in a potential, so h has just eigenstate, energy eigenstates. Eigenstates. Okay? And the ground state is the lowest energy state. It has an energy E naught. That's the energy of the ground state. Okay, so of course, then this can be diagonalized. It is sum over n of exponential of minus tau over h bar E n times the projection onto the ground state. You see? Okay, so now you see immediately that when tau goes to infinity, plus infinity, the dominant term is a term such that this is the smallest. So when t goes to infinity, this is the same an exponential of minus tau over h bar e naught times the projection on the ground state. This is quite easy to see. Okay. Now, what does this correspond to in terms of a path integral? Okay. In terms of a path integral, let me assume that I am just interested into well, in the path integral, remember that computing, for instance, the partition function, z equal trace of exponential of u e of tau is just given by a path integral with a real factor given by the exponential of minus the Euclidean action. So remember, the Euclidean action differs from the real-time action by a plus sign in front of v instead of a minus sign. Okay, but very importantly, with over periodic trajectories in Euclidean time, such that q of sigma plus tau h bar over, well, basically equal q of sigma. So we have a period periodic Euclidean time tau. So you must consider that, in fact, the trajectory close onto themselves. Okay. And therefore, so you must consider that, in fact, for instance, the time is closed, if you want. Euclidean time is closed. 0 tau. This is Euclidean time. And everything that we compute is for trajectories that are Euclidean, that are periodic in time. And therefore, now if, for instance, we want to compute, for instance, in a thermal state, if we want to compute what is the expectation value on some observable, let us say, well, q is not a good observable, but some function f of q in a thermal state characterized by beta 1 over kBt, we know that this is trace of f of q ue of h bar beta divided by trace of ue of h bar beta. And applying what we did that, this object is simply given by the same path integral over periodic trajectories, where we insert the function f of the position of the particle at any given time, let us say time 0, Euclidean time sigma equals 0, because this is not important. Okay, so that's the numerator. the numerator is given also by a path integral where we insert the function f of the position q at time 0, and we divide by this path integral. Without the insertion of the operator. So we just insert observable f of q, where f is some function, f some bounded function. Okay? And period tau beta equal h bar over kb times the temperature. Yes?
Can you explain why we singled out time 0, sigma equals 0?
Oh, that's because if I can choose any time sigma here, and the result of the integral will be the same because we can make a Euclidean time translation without changing the integrand. This doesn't change, this doesn't change. So this is independent of sigma. Just because we are considering one observable. If we were considering a product of observable at different Euclidean time, then the situation would be different. Okay. Okay, and so you see that if we want to compute, so now, if we want to compute the ground state matrix element of this observable f of q, so we want to compute the expectation value of the observable f of q, where q now is a quantum operator on the ground state. This is a vacuum expectation value. What do we have to do? We have to compute this path integral, but we simply have to project on the ground state by taking the limit tau beta equal infinite. So you see, which means that we replace periodic Euclidean time by infinite here we have periodic. So if we perform a path integral calculation at Euclidean time with an infinite Euclidean time, so not taking it, forgetting that Euclidean time is periodic, what we compute is automatically, if we take the ratio of those two quantities, of course, to normalize so that this is a probability distribution, we automatically compute expectation value observable on the ground state. If you want to compute expectation value in some other states, you have to work more. But ground state expectation value are automatically evaluated by doing an Euclidean time path integral in infinite Euclidean time. So that's very simple. Okay. See? So this seems a bit abstract, but we shall use heavily those two simple observations when quantizing the scalar field. So I have about 20 minutes. So now let me turn to, if there are no questions, let me turn to quantization of the scalar free field. Okay, so what is a scalar free field? You have studied it in the QFT1 course. Chop, 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 chop. Here it is. The scalar free field is just the object, classically, the object that describes Klein-Gordon particle. So it describes scalar particles of mass m, spin 0, and for the free field, non-interacting. But second quantized. So the Hilbert space is a Fock space built out of the states of a one particle of mass m. And of course, relativistic. So it's relativistic, and it obeys the Bose-Einstein statistics. So you may have as many particles at a given point of space or in a given quantum state as you like. Okay. So this is a quantum state. What is the classical theory of that? The classical theory is just a field phi depending on a vector in space-time. So phi of x is a real variable, scalar, and x contains the time and the position, and or it's written as x mu, mu equal, and let me use the notation 0 to d minus 1. So x naught is time, and x1 up to xd minus 1 is space. Okay? So I have, I am in 1 plus d minus 1 dimensions. And again, let me remind that I am going to use a notation. D is ds squared equal minus dt squared plus dx squared. So the signature of space-time is minus, plus, plus, plus. Okay? So now, what is the classical action for this free field? It's given by an integral over d time, an integral over space of a Lagrangian density. And what is the Lagrangian density? It is 1/2 of dt of phi squared minus 1/2 of d gradient with respect to the position of x minus m squared over 2 phi squared. So this is the Lagrangian density, and this is the classical action for the scalar free field. Okay? And we can rewrite this in covariant notation as integral over d of x over the whole dimension here d of minus 1/2 d mu phi minus 1 over 2 m squared phi squared. Okay.
Positive 1/2 d mu phi d mu phi.
Pardon?
We're using the signature of
Oh,
That's because of the signature.
okay.
Warning. Signature. Okay. So before going to quantization, this is the theory at real time. But we may play the game of looking out at what is this theory at Euclidean time, because we are going, for instance, to study the thermal property of the thermal states of a quantum field. And in fact, that's something that's very useful if you do cosmology, or if you are doing studying heavy ion collision, where you create a plasma of particles, of quarks and gluons, And if you, for some period of the collision, it can be described by some equilibrium or quasi-equilibrium state at a finite temperature, and then you need to study a quantum field theory at finite temperature, in a finite temperature state. Okay, so what is it at Euclidean time? Okay, well, you know the rule. You change t into minus I times tau, where tau now is Euclidean time. Tau, t is a real time. And then, of course, d2s becomes, as I explained yesterday, d tau squared plus d x squared. So that's the Euclidean matrix on the d-dimensional Euclidean space. And what is the Euclidean action? Remember the rule. The Euclidean action of phi is defined as minus I times the action at real time when you do this change of variables. And there is a minus I. There is an I factor that comes from this change of variables. Well, there is a minus I factor that comes from this change of variables. There is a minus sign that comes from this change of variables. Here, the signs do not change because we do not change x and these terms. And if you do the calculation, what you come out is that with something which is positive, which is d of x. Let me write it x Euclidean by writing that x Euclidean is a vector tau x. So this is a d-dimensional vector in Euclidean space of 1/2 of d mu phi plus m squared over 2 phi squared. So the Euclidean action is something that is positive. Yes?
When you change from real time to Euclidean time, we're assuming that the field doesn't change by doing that kind of rescaling of time.
Well, at that moment, this field is just a function of some variables, and I'm writing something abstract. Now, of course, if you are considering a physical realization, a given mathematical realization that depends both on t and x, what you are to assume is that this function, as a function of time, you have a function phi of t, and you assume that it can be analytically continued in the lower half plane. Of course, for a given configuration of the field, that's in general not the case. You take a function, it has many analytical continuation, or it has no analytical continuation. But if you take a solution of the equation of motion, for instance, if you take a solution, well, the equation of motion here will be d over dt, d2 over dt squared of phi squared plus d2 over dx squared of phi, I'm sorry, plus m squared phi. Or if you can go in Fourier transform and write that phi hat of omega k exponential is given by you realize that the solution of the equation of motion are just plane waves. So they depends as exponential I omega t or exponential minus I omega t with omega squared equal k squared plus m squared. And these exponential, you can analytically continue them. So for a specific solution of the equation of motion, you can make an analytic continuation.
There's another question. So you're considering the action. When we derive the path integral formulation for this
yes.
probability amplitude, it worked out fine because the Hamiltonian was simple enough so that
Yes.
we concluded that it was the action.
Yes.
Right? Why in this case is this also valid?
It's fun because no, it works because in fact the calculation I presented it in a very sketchy way, and you did it in a more detailed way in the quantum theory course. Works as well if you are careful enough if you take a more complicated theory. And in fact, you can do that in this case. Let me explain how it works, and then possibly that will stop. Let me explain how it works. If you want to work carefully.
Can you repeat what the question is? What the query being addressed here? I don't understand what the question is.
The question is, why does the recipe to express probability amplitude, transition amplitude in a simple quantum theory as a path integral works for a more complicated theory that has an infinite number of degrees of freedom? That's the point. And I will explain how you can convince yourself, in fact, prove that it works. So we start from phi of t and x that has an infinite number of degrees of freedom. Because there is one phi at each point of space. Okay. And it's an infinite continuum number of degrees of freedom. But if you want to be careful, you can make a discrete number of degrees of freedom so that you feel on safer ground by just discretize space. You see. So let me represent, this is time, this is space, and I assume that I am in dimension d equal 2, but you can do the same thing for higher dimension. Okay. So do that. Assume that instead of having a continuum space, you have a discrete space, so a lattice here, one-dimensional lattice of points with a lattice spacing delta x. Okay. Then replace this action simply by s of phi equal, of course, integral over dt, then sum over I So you replace the integral over dx by a sum over I delta x. You replace, of course, you have 1 over, and assume that phi of t and xi, I redefine this as phi I of t. So here I have a discrete number of variables. So then I can revise this as 1/2 d over dt of phi I squared. And then I want to discretize my derivative term. I can discretize it by simply that phi I plus 1 minus phi I squared divided by delta x squared. So that's a natural discretization of the space derivative by finite difference derivative. And then minus m squared over 2 phi I squared. Okay. So here you have something which looks very much like just an harmonic oscillator, but you have a collection. This is the action of an harmonic oscillator. So you have an infinite number of harmonic oscillators labeled by I, but they are coupled. Coupled ensemble of oscillators. Okay. And I hope you will be convinced by the fact that for that you can apply the path integral recipe. If you are not yet satisfied because this couples the Hamiltonian, just change of base so that this becomes diagonal. You take the Fourier transform of phi high, then this becomes diagonal. So you can separate that into decoupled modes. You can decouple that into decoupled modes phi k with some k discrete. Well, k in some Brillouin zone of the lattice. And since they are decoupled, you have a collection of decoupled harmonic modes. You apply the recipe, then you Fourier transform back. So you can replace in the path integral the continuum action by, I have not written yet the path integral, but okay, so you can do that. Okay, so here is the recipe. Okay, so now apply so now the use is apply the path integral recipe. Then you obtain a functional integral over fields configuration with a phase factor which is exponential of I over h bar s of phi with a measure that has to be defined. And if you want to know exactly what you are doing, here is how it goes. This is the mid. Remember, in order to define properly what is the path integral formulation, you have to discretize time also with a time step delta t. So then t equal g delta t with g integer. X is I delta x, Iz. So we have a two-dimensional lattice C2. Space-time become a lattice. Not only space, space-time is considered as a lattice. And then phi of Ti, this is Ti, Tg, Tg xi, you consider that is phi of some vector I with I belonging to Z2. You see? And then you can discretize S of phi discretized as sum over G delta t, sum over I delta x. Then you discretize also the time derivative, as we did for the harmonic oscillator. You get 1/2 phi g plus 1 I minus phi g I over delta t squared minus 1/2 phi of g I plus 1 minus phi g I divided by delta x squared minus m squared over 2 phi of I g squared. And that's, if you want, a finite, or at least an integral over a discrete number of degrees of freedom. Okay? So this is, in fact, the limit when delta t goes to 0 and delta x goes to 0. We know that the path integral is defined as a limit of something discrete when delta t goes to 0. We discretize space also in order to be sure to manipulate well-defined quantity, but in order to define, to get back continuum space-time with a delta x of 0 of something which is, and then the measure, if you apply the recipe of the path integral formalism, you sum over, and in general, if you are in d dimension, let's go back to d dimensions. If you apply the result, the recipe, you see that this measure d phi of x is simply a product of flat measure over d phi I at each point with a factor which is 2 pi I h bar delta t over delta x. Well, in that case, if you are in d dimension, the delta x is replaced by delta x to the power d minus 1. And if you do the calculation, if I am not mistaken, you get delta x to the power d minus 1. Let me check. I am never sure. Yes. That's it. To the power minus 1/2. So this is correct d of phi of x measure times exponential of I over h bar, this action discretized over the phi I. Okay. And we obtain that just by being careful and applying the path integral recipe. Okay? But it's better to write it in this way because in all the calculation, we can do the calculation directly in this continuum space-time limit. So discretization of space and discretization of time was just an intermediate steps to define things properly. And you see, discretization of time was just the discretization originally used by Feynman in this derivation, and you can find it already in his famous book, Feynman and Hibbs. There is a, okay? The idea of discretizing space to define a continuum theory, in fact, is a bit more fancy, but in fact, I think it's even older because it was proposed by Heisenberg very early in the 30s in order to trying to get rid of some problem in quantizing the Maxwell field. So it's an old idea which was revived a lot of time. Okay. But here this, discretizing space and time is just a mathematical recipe. At the end, we built out a theory in a continuum space-time. Okay. So now basically we have defined a functional integral over field in space-time, scalar fields in space-time. See? And I will end up here, and we'll use this formulation in the next course. Simply two remarks. First, this action is still quadratic in the phi. So this is still a Gaussian integral. That's because we are considering the free field, non-interacting field. But still, we are still just making a calculation over a Gaussian integral, simply a Gaussian involving a continuum infinite number of variables, but still a Gaussian integral. And therefore, all the mathematical rules to compute expectation value of object with a probability density which is Gaussian apply, which makes calculation quite simple. Okay? And finally, last remark. This works as well at Euclidean time. At Euclidean time, you simply have to consider, for instance, a partition function given by d of phi of x, but now x has to be taken as an Euclidean vector, exponential of minus 1 over h bar se of phi, and still a Gaussian integral. And here, a really Gaussian integral with exponential of minus a positive quadratic form. Here you have I phases, so you have to be a bit careful. But here it works very well. So here we have something well defined. Yes? And finally, yes, you may ask a question. What about finite temperature? Then remember Euclidean spacetime. Euclidean spacetime depends on tau and x, or if you prefer, x naught and x mu, mu equal 1, v minus 1. Okay, so finite temperature means that phi of tau and x has to be periodic in time, but not in space. So space-time, two-dimensional or d-dimensional space-time, Euclidean space-time, has to be considered as something periodic in Euclidean time tau, with a period tau beta equal h bar over kBt as usual, but infinite in space. Yes?
So in what sense does interaction with some sort of thermal, why does it break the symmetry between space and time? Now, like
that's because thermal states are not Lorentz invariant. Thermal states means that your system, here a quantum field, is in equilibrium with another big system defined in space-time, that is a thermostat. So imagine that, for instance, you have another field in a highly excited state, and your quantum field exchanges energy with this quantum state. But excited states for the thermostat cannot be Lorentz invariant. You will see later, I think you have seen that in the QFT1 course. The only quantum state of a quantum field that is Lorentz invariant is the vacuum state, I think. Or if you have a particle, a particle state, it must have some impulsion, you know, in momentum space, where this is k and this is the energy. This is the ground state, and this is the light cone, And this is one particle state. The one particle states live on some, the first, the shell, the one particle shell. So one particle state is a point living there. It's characterized by some energy, some momenta with E squared equal k squared plus m squared. If you make, and here is the vacuum state. If you make a Lorentz boost, this goes somewhere else. It's not Lorentz invariant. Only the vacuum state is Lorentz invariant. So it makes sense to speak of thermal states in quantum field theory, but these are not Lorentz invariant. You must, when you say that a state is a quantum state characterized by some temperature at equilibrium, it is at equilibrium in a given Lorentz frame. If you go to another Lorentz frame, it's not anymore at equilibrium. Okay? And you see that immediately by saying that if you have space-time that is a cylinder, well, you can have, well, in Euclidean time, Lorentz transformation becomes just Euclidean transformation, translation and rotation. And if you have a cylinder, you cannot make a rotation like that. You can make a translation. You can make a translation in time, but you cannot rotate a cylinder. So that's what you probably what you meant. The geometry of Euclidean spacetime that describes a thermal state is not invariant under rotation because there is one special direction, which is the infinite direction in space. Okay? Okay. So, well, tomorrow, we'll see how, starting from this seemingly very abstract and complicated path integral, we can compute very easily a lot of observable of the free quantum field. And doing that, you will recover in a very fast way quantities that you have computed in the quantum field theory 1 course using the canonical formalism of creation and annihilation operator acting on the Fock space of the particle, built out of the one particle state of particle. Okay? So, thank you.